Hi, my name is Dr. Deshawn. In this video, we are going to differentiate a variable base to a variable exponent using logarithmic differentiation. So here is the process that you need to go through. If you have a variable base, variable exponent, and you need to find a derivative of a function that looks like that, first thing we're going to do is we're going to natural log both sides of our equation, okay? Then we're going to use our properties of natural logs to simplify the right-hand side of the equation because we're going to assume that it's in y equals form. Then we're going to differentiate both sides of the equation with respect to x, implicitly differentiate both sides with respect to x. So the left-hand side, you'll end up with a 1 over y times dy dx, and we'll show that in an example. And the right-hand side, we're going to use the product rule. And then once we're done differentiating, we're going to solve for dy dx, our derivative, and write our answer in simplest form. All right, so let's see all these steps with an example. So here's example number 1. This is Remy and Rosie. Come here, Remy, you're such an obedient student, aren't you? Okay, so first thing we want to do, we want to find the derivative, okay? So derivative, when you have a variable base and a variable exponent, you can't use the power rule and you can't use the exponential rule. You have to follow this logarithmic differentiation process, okay? So the first thing we want to do is natural log of both sides of the equation. So we're going to natural log the left side, so we have ln y on the left, and we're going to natural log the right-hand side. So we have natural log of x raised to the x minus 1 power. We want to natural log both sides of the equation. Once we finish natural log both sides of the equation, we want to go to the right-hand side. We're going to use our properties to simplify. Now, what does it say we can do? It says we can take this exponent here and we can drop this exponent around front, okay? So the left-hand side, we still have natural log y on the left. The right-hand side, x minus 1 times the natural log of x. All right, simplify using the properties. Now we're ready to differentiate both sides of the equation with respect to x. Left-hand side, we have natural log y. How do we differentiate a natural log? We want to take the derivative of this over the derivative of y is 1, right, over y, and that's the derivative of y with respect to x because we need to differentiate implicitly both sides of the equation with respect to x, okay? So here we go on the left-hand side, 1 over y dy dx. Because it's y equals, you natural log both sides, you're going to have ln y equals. So the left-hand side, you're going to have 1 over y dy dx on the left-hand side, okay? Right-hand side, we need to use the product rule. We have an x minus 1 multiplied by natural log x. Use the product rule, which says take the x minus 1 first, bring that down, product rule, times the derivative of ln x, so u prime over u, so 1 over x, okay? Plus, then you're going to bring the natural log function down, times the derivative of x minus 1, which is just 1, all right? Product rule on the right. Product rule, when you have a u times v, your product rule is going to be u v prime plus v u prime, all right? So we're right here, all right? Let's simplify. I've got a lot of grouping symbols on the right-hand side, so let's go ahead. 1 over y dy dx on the left, okay? On the right-hand side, well, let's call this x minus 1 over x plus natural log x. So you just remove the grouping symbols, all right? And then what? We are solving for dy dx. We don't want 1 over y dy dx, we want to just have dy dx, okay? So what do we need to do to get dy dx by itself? We need to multiply both sides. We need to multiply both sides of our equation by y, all right? But we're going to make a substitution here, all right? So let's take a look. Left-hand side, the y's cancel, so here's our dy dx, all right? And then the right-hand side, we have in grouping symbols, we have x minus 1 over x plus natural log x times y, but we're going to substitute for y. Go up here to the original problem that we were given. We're going to take that y, substitute in for y, x raised to the x minus 1 power, and here is how we differentiate a function that has a variable base and a variable exponent, all right? So this is what our answer looks like, all right? So logarithmic differentiation, if you have a variable base, variable exponent, we use logarithmic differentiation, okay? So we're going to natural log both sides of the equation. Use your properties on the right-hand side to simplify. All right, after those two steps, differentiate both sides. Left side, 1 over y dy dx. Right-hand side, use the product rule. all right? And then simplifying, solve for dy dx. So here are the steps to going through the process, all right? On the back of the board, I have another example for us. So let's go ahead and take a look at one more example, all right? So let me see if I can get the board to flip around. All righty, good girl, Rosie. All right, so let's try this example, a little bit more involved. Okay, and the steps are on the other side, so let's see if you remember the steps, okay? So y equals x raised to the 3 over x power. We have an equation here, function here. We have a variable base and a variable exponent, okay? Can't use the power rule, can't use exponential rule, not when the variable's in the base and the exponent, so you have to use logarithmic differentiation. So remember how that works? Well, how do we start? We natural log the left, natural log the right, natural log both sides of the equation. ln equals natural log of x raised to the 3 over x, okay? All right, why are we doing that? Because that allows us to take this exponent and bring it around front. Properties of logarithms. So you have on the left side ln y, on the right side 3 over x, natural log x, all right? Then we differentiate implicitly both sides of the equation with respect to x. Left side gives us 1 over y, u prime over u, times dy dx. And then the right-hand side, we have to use the product rule. So we're going to take the first function, 3 over x, times the derivative of ln x. It's 1 over x, okay? Plus take that second function, natural log x, multiply by the derivative of 3 over x. What's the derivative of 3 over x? That's 3x to the negative 1 power. Using the power rule, you're going to get negative 3 over x squared. There's your derivative. That's the derivative, all right? The derivative of 3 over x, okay, is equal to the derivative of 3x to the negative 1, okay? So using the power rule here, you can see it's going to be negative 3x to the negative 2 power, which gives us negative 3 over x squared, okay? All right, so just a little explanation for that piece there. So we differentiated both sides, okay? And let's clean it up a little bit. So 1 over y, dy dx on the left. All right, what do we have over here? It looks like 3 over x squared. And then this is a minus, okay? So this is a minus 3 natural log x over x squared. All right, so when we remove the grouping symbols and combine the terms, we have this, okay? So we want to solve for dy dx. We're looking for the derivative, not 1 over y dy dx. So multiply both sides by y, all right? So we can get dy dx by itself. So we want to multiply both sides of the equation by y. So finally our answer is going to be, so we have dy dx is equal to, well, they have the same denominator, so I can keep the denominator. All right, and I can combine those numerators, 3 minus 3 ln x, okay? And then multiply that by y, but remember, we're not going to put the y here. We're going to actually go up and substitute in x to the 3 over x power, all right? And you could, bring this up and keep the base, subtract the exponent. You could write this quantity times x to the 3 over x minus 2 if you wanted to just write it one string in terms, but ran out of space on this one. So, but that is the process, okay? So there's the process when you have a variable base, variable exponent. That is the process you would use to differentiate, all right? As opposed to, let's take a look at the other two rules, okay? So what if you had y equals x to the 3rd power? We want the derivative x to the 3rd, all right? Well, if you have a variable base and a number for the exponent, we can just use our power rule, all right? Do you remember what that power rule was? Just to put this in perspective, all right? So the power rule is when you're finding the derivative of x to the n, okay, it's going to be n times x to the n minus 1 power. We can just use the power rule, all right? So power rule, so this derivative, dy dx, okay, bring the 3 around front, times x to the 2nd power. You can use the power rule when it's a variable base and a number exponent, power rule. If you have a variable base and a variable in the exponent, you can't use the power rule. You have to use logarithmic differentiation, all right? Now, something cool to see, okay? So this problem over here is done, and let me just draw, okay? So something cool to see. What if I took y equals x to the 3rd? What if I took y equals x to the third and I use logarithmic differentiation? Okay, can I use it on this? Natural log both sides, ln y, ln x cubed. Natural log both sides. Use your properties to simplify. Left side, ln y. The right side is going to be 3. Bring the 3 around front times natural log x. Use your properties to simplify. All right, differentiate both sides. Your left-hand side will always be 1 over y dy dx, and your right-hand side is going to be 3 times 1 over x. We don't need the product rule here, okay? So the product, we just have to differentiate both sides, okay? And then we want to solve for dy dx. We're going to multiply both sides by y, so dy dx, okay, what do we have over here? We have 3 over x, and that needs to be multiplied by y, and y is x to the third power. All right, and when you multiply those, you see one of the x's cancels, and so your dy dx, okay, gives you 3x squared. All right, so it gives you 3x squared. So basically, you can use logarithmic differentiation on anything. It works for every type of function. All right, it works for every type of function. You can use logarithmic differentiation on power rule, as I just showed you, product rule, quotient rule, exponential, and so on, okay? It works on everything. But if you have a variable base and a variable exponent, you have to use it there. You have to, okay? Variable base with a number exponent, you can use the power rule, all right? What if you have a number base and a variable exponent, okay? Let's just address that too, okay? So what if you have a number base and a variable exponent? What if you have an exponential function, all right? 5 raised to the 2x power. This is an exponential function. When you have a number in the base and a variable in the exponent, it's an exponential function. All right. So how would you differentiate this? All right. This is considered an a to the u. Okay. It's an exponential function. So your rule here is you bring the entire exponential function over, multiply that by the derivative of the exponent, multiply that by natural log the base. Okay. A lot of pieces to this. Okay. But that's how you would actually use, this is the rule you would use here, all right? So what does this dy dx look like? All right, well, it's got a lot of pieces to it because it's exponential. You bring the entire exponential function down times the derivative of the exponent, and then you natural log the base, okay? So this is how you actually find the derivative of an exponential function, all right? This is your derivative of the exponential function right here, okay? But can I use logarithmic differentiation? There's a lot of pieces to this formula. What if I don't remember all the pieces, okay? Logarithmic differentiation, I know the process is a little bit longer, but sometimes it'll save the day if you forgot your formulas, okay? So let's do it, okay? So you have 5 to the 2x, all right? Natural log both sides, natural log y, natural log 5 to the 2x power, natural log both sides, okay? Use your properties to simplify that. 2x comes around front, so the left side natural log y and the right side 2x times the natural log of 5. All right, differentiate both sides of the equation. Left-hand side is going to be 1 over y dy dx. Differentiate both sides of the equation with respect to x, implicitly with respect to x. Okay, right-hand side, 2 and ln 5 are constants. When you have a constant times x and you take the derivative, it's just the constant. It's 2 ln 5, and that's the derivative of the right-hand side, okay? And we don't want 1 over y dy dx, we just want dy dx, okay? So multiply both sides by y. Multiply, you get 2 ln 5, and then times y, but instead of y, we are going to put in 5 to the 2x, okay? So here you see, you have all your pieces, you have the entire exponential function, times the derivative of the exponent times natural log the base, all right? So if you have a variable base number exponent, just use the power rule. We have those proven to be true theorems, so just use the power rule, it's easier, okay? If you have an exponential function, number in the base variable in the exponent, all right, just use your exponential rule. Theorems, these are theorems that have been proven to be true, exponential rule, all right? What if you have a variable in the base and the variable in the exponent, okay? Variable raised to a variable power, you have to use logarithmic differentiation. This is where you have to use it, okay? Point I'm trying to make here is logarithmic differentiation works on everything, okay? You can use logarithmic differentiation anytime you want, but you know, variable base number exponent, use the power rule. number in the base, variable in the exponent, use your exponential rule. If you have a variable to a variable, logarithmic differentiation. And that's how it works, and a little bit of an expansion on this topic. All right. Well, thank you so much for watching, and take care.